Testing, 1, 2, 3. Testing. All right, everybody. Welcome to my second video of my differential and integral calculus series. In today's video, we'll recap some of the interesting new pieces of notation that we learned. And we'll also continue on our quest of mastering the notation required to succeed in differential and integral calculus. So first, we're going to recap some of the notation we learned in yesterday's video. Let me just increase the size of this pen. 2, we're going to learn about interval notation, which is really a fancy way of describing our domain and range. And 3, because I always like to have 3 objectives. No matter the video, you will see that'll become a tradition of mine. We're going to do some examples. It's basically a 2a here. But let's humor me here and let's say it's a 3. Which means we're going to do some examples. And excuse me if, don't mind if I switch the notation. Don't mind if I switch the thickness of the pen. We're not switching the notation, that's for sure not. All right, let's go. To begin, let's recap what we learned about yesterday. We learned that a function maps one input to one output. And a way I like to describe this is kind of like a machine. If we put this pizza, that's my pizza, into this oven, there's a little fire burning inside because we like wood burn pizza. If we put our pizza into the oven, we're going to get cooked pizza. And that's my cooked pizza. It looks kind of like the Japanese flag. Let's get a better example. For all my baseball fans out here, if I put a baseball into, let's say, a batter's sweet spot, this is kind of more abstract, but if I put a baseball into a batter's sweet spot, and our machine here is called swing, then our ball is going to become a home run. Let's put into the stands. Yay. These are my people in the stands waiting for the home run. So these are more abstract examples, but if you're familiar with the idea, you'll see that we're putting an object or a number into something, into a machine that's going to transform our input into an output. Let's use numbers. And I won't spend too long on this because we do have some more notation to learn and get through today. But if I put a number, let's say 3, into a function that we're very familiar with, which is a square root function, where x is a placeholder, I can put any letter I want in under that square root. We just like to use x. If I put 3 into the square root, let's change this. Let's say 9. Some of you may have picked up why. If I put 9 into my square root function, well, I get root 9, which is equal to 3. So again, there's this direct transformation between the input and the output. And in this abstract example, it's the same. I'm putting an input into a function, and I've assigned this function to be the swing, the hitter's swing. So if I put the ball into a function that says swing, the hitter's going to swing the bat, and hit the ball for a home run. Exact same thing going on here. It is going on here. If I put my pizza into an oven, it's going to become cooked pizza. All right, that's a function. If you have any questions, do leave a comment on this video or send me an email if I do put that in the description. In any case, before we do an example here, let's learn some more notation before I get to interval notation. It's a little bit dark here, if you'll excuse me. Let's learn what R means. This fancy R. Really, it's an R with a thick handle right here, thick handlebar. R means the real numbers. And a quick diagram I like to use not to get sidetracked when describing the different kinds of numbers is to do something like this. In the beginning of our circle, or let's say the center, at the center of our circle, we have the natural numbers. Let's say they're n. And by natural, I mean regular. Let's think about that as a regular number. 1, 2, 3, 4. Then we have the integers. And by integers, I mean the natural numbers, except to make them negative. Etc. Next, we have the rational numbers, which are our fractions. And if you notice, let me just give you an example. If you notice that the rational numbers contain or include the natural numbers, they include the integers. What I mean by that is, look at a rational number can be negative. A rational number can technically be an integer. It can be negative too. And a rational number can also be 2, except we have a more precise way of classifying 2 as a natural number. But what I'm really trying to get at is that the rational numbers include the natural numbers. They include the integers. But the natural number, or a rational number cannot be a natural number. And an integer cannot be a rational number. An integer can be a rational number. A rational number can be an integer. But an integer cannot be a rational number. You know what? I might have to get back to you on that, because that is confusing. What I'm really trying to get at is that the natural numbers are a set within the integers. And the integers are set within the rational numbers. So an integer can be a rational number, and a natural number can be a rational number, but a rational number cannot be a natural number. Okay? That's what we're trying to get at. That's the direction it goes at and goes in. In any case, if you were bogged down by that, forget I mentioned that. That's something you can look up on your own time in more detail. Returning to notation, really all I wanted to include here was that when we say f goes from R to R, we see that f is mapped in the real numbers. If you can read that. Let's give an example. That's x squared. What's our domain of f? Well, our domain of f is actually the real numbers. We can put any number into our f of x function, and we get an output. And now you're probably thinking, hey, John, isn't every function's domain the real numbers? Well, no. If I had something like this, if I had something like that, and I had an asymptote, which we'll get at later, or maybe you've seen the asymptote. It is a number that the graph approaches but never hits. If I had something like this, so our domain would be negative infinity, so it would be these brackets here, 2, 0. And that's a very good segue into our next topic for the day. But before I get there, let me just remind you that the range of that other function up here is what? X is greater than or equal to 0. And if we really want it to be fancy, we can use our fancy knowledge here. We can use our fancy knowledge we learned that by saying x is a member of the reals such that x is greater than 0. Usually we like to say y. Usually we'd say f of x is a member of the reals such that x is greater than or equal to 0. But theoretically, we can use any letter we want for x. Anyways, the whole point of this video is to introduce to you set notation. Set notation is a way of grouping numbers together in a convenient way. And so interval notation, we have a few different examples. We have the 2 square brackets, the 2 curved brackets, and we have one of each. Really quickly, if I had a number line, and I had the numbers 1, 2, 3. And each of the numbers were a part of my set. If 1 and 3 were included in my set, we would write 1, 3, and that includes 2. Really powerful stuff, If I had the same number line, but I did not want to include 1 and 3. I did not want to include 1 and 3 in my interval. Then I could write it as such. And 1, 3, what 1, 3 really means is 2. Because it is called an open interval. This is called a closed interval. So a closed interval includes the numbers. It's kind of like a box. You're putting something in a box. The 2 is in the box. The 1 is in the box. The 3 is in the box. But in the open interval, only the 2 is in the box. And if I have one of each, can you figure out what I mean? If I have 1 included. If I draw my number line again, 1, 2, 3. If I want my 1 included, I want my 3 excluded, then really all I have is 1 and 2. So if we were to apply what we just learned for domain and range, or if we were to, connect domain and range to interval notation to do it, what's the domain and range of x squared using interval notation? Well, our domain is going to be negative infinity to positive infinity. Infinity isn't a number, so how can we put infinity in a box? We don't have anything in a box. We have every single number. We actually have, going up here, we have all the real numbers in a box. Not the rational numbers, the real numbers. In a box. But we don't have infinity, because how can we put infinity into a box if infinity is not a number? The range, let me ask you this, is 0 Let's give you this. Let's go 0 to infinity. Are we going to have a closed or an open bracket next to 0? Well, closed, because 0 is included. When we put 0 into x squared, we get 0. But again, what do we have around infinity? Well, we have this, because we can't trap infinity into a box. And that's all I'd like to cover. Let's recap. Interval notation, we covered. We'll do a few more examples next time. Let's put a box around it. We recapped interval notation. Before we get to the recap, let's go over this again. A function. You have an input. You put it into a machine. Our machine in this case is a pizza oven. And we turn our pizza into cooked pizza. The machine in this example is our swing. If we put a ball into a baseball player's swing, if we put it into a machine that tells the baseball player to swing, we're going to get a home run. And mathematically, a fine example of this is if we put 9 into our square root of x function, we're going to get the square root of 9, which is 3. If we put any other number, if we put 2, 3, 4, 5, 6, 7, 8, any other number, we will always get a distinct output, which is the beauty of a function. If we're being technical here, if I put a ball into the function that's a swing, is this really a function? No, because each input can correspond to multiple outputs. We can get a ground ball. We can get a pop out. We can get a line drive. And so this ball can map to many different inputs. Many different outputs, excuse me, and that's no good. We did a little aside here about the natural integers and real numbers. And a natural number, 1, 2, 3, 4. Integers, make that negative. Rational numbers, make that fraction. A natural number is a set included in the integers. It is included in the real numbers. But a real number, a real number cannot, we can't go the other way. A real number is not an integer. A real number cannot be included in the natural numbers, because this is my example I'll use. How can I have 4 over 3 as a natural number? I can have 1. I can rewrite 1 as 1 over 1. I can rewrite 2 as 4 over 2. That's a real number. It's a rational number. So that's a, am I confusing you guys? These are the real numbers. Excuse me. This R is rational. This makes up the real numbers. Yep. And we have this little funny box here called irrational numbers, which includes something like pi. But that's an aside. In any case, the rational numbers cannot be expressed as natural numbers, but the natural numbers can certainly be expressed as rational numbers. Rational numbers. Okay. And then we have the main point for today, which is our interval notation. Building off that domain and range discussion from last video, if I put square brackets, I have a closed interval, which means I want to include all 3 numbers in my box. If I have open brackets, I only include the number in the middle. I do not include the 1 or the 3. And if I have one of each, you know the drill. 1's included, 2 is in my box, but 3 is not included. That's it for today's video. Thank you very much for your attention. I do hope this helps. I do hope you enjoyed the content, and I'll see you in the next one. Peace.